if you want to go check those out. But I'll probably pass them back here in the next couple days. We are starting for 4, and this is a decently long section. We're going to actually start to evaluate definite integrals today with the fundamental theorem of calculus. Instead of just setting them up, we'll actually kind of learn how to use them. So this is just part 1. I think there's like 4 or 5 parts to this section. So I need to tell you, first of all, what the fundamental theorem of calculus says. So, very important here for how to evaluate definite integrals. And it says, if you integrate from A to B, so again, A is the lower bound, B is the upper bound. Everything I'm doing today is in terms of x, by the way. You won't have to integrate with respect to y. But it says the integral from A to B of f of x dx equals capital F of B minus capital F of A. F of B minus F of A. Now, notice this is capitalized and this is not. So I want to make sure you know, first of all, that what they're doing right here is not just plugging in the upper bound to the original function and then the lower bound to the original function. That's not what's happening. The capital F, and I think I've actually got this labeled here, the capital F is the function after you integrate. So you have to integrate first, bless you, and then whatever you get once you integrate, the first thing to do is plug in the upper bound minus plugging in the lower bound. And then actually at that point, since you're plugging in numbers, you should get back a number. That's kind of the big difference here. With indefinite integrals, when you didn't have the A and the B, your answer was always something in terms of x or whatever variable that was. But with definite integrals, these are going to be numbers, and once you plug them in, you just get back an actual number. And this kind of goes back to the idea of finding the area. Now that you know what A is and you know what B is, then that is kind of like you're finding the area between the function and the x-axis. So seeing it like that maybe doesn't make a whole lot of sense just yet. Once we do the examples, you'll kind of see where the capital F is and then how to plug in those numbers. So directions now say evaluate the definite integral. Difference between indefinite and definite is just the fact that there's an upper bound and a lower bound. So here is example 1. It says we are integrating from -1 to 2 of x squared plus 2 dx. That's our function. Upper bound is 2, lower bound is -1. Now, the first thing you should do is actually integrate. So I'm not really concerned about the -1 and the +2 right now. I'm just going to take this function and integrate it. So add 1 to my power, put my new power on bottom. That becomes x cubed over 3. Plus, if I integrate 2, what would I get? 2x. Now here's another difference between the indefinite integrals and the definites. We don't have to put plus c here. We're not trying to guess what that function was. We're actually going to plug in numbers for x. So here's kind of the general notation that we use when we set this up. Most of the time after you integrate, you can set up kind of like a bracket over there and go ahead back on and put the -1 and the +2. Now, probably the most common mistake of evaluating definite integrals is plugging in the wrong number first. If you go back to the fundamental theorem of calculus, I'm reversing here, it says capital F of B minus capital F of A. You have to plug in the upper bound first. So, in our case, this is B and that is A. So let's take this is kind of like the capital F right here. Let's take that and plug in the 2 first. Wherever I see X, I'm replacing it with 2. Okie doke. Now I have to subtract whatever I get back from plugging in the -1. Now, this is probably one of the other most common mistakes, the subtraction. Anytime what you got after you integrated is like a sum or a difference like that is, I would suggest kind of setting up some parentheses right after that minus sign, because you're going to have to subtract all of it. So the minus is going to have to go to both of those terms. I guess you could go ahead and distribute it if you wanted, but I'll just do it like that for now. And then wherever I see X, plug in a -1. So that's -1 cubed over 3 plus 2 times -1. Now we just have to go through and evaluate. 2 cubed is 8. So this is 8/3 plus 4. Now, I don't like to do too much at once. I'm afraid I'm going to lose a negative somewhere. So let me just simplify this stuff real quick. If I cube a negative, it's still negative. So that's still -1/3. And that would become a -2. But by the time I distribute this minus sign, I'm going to draw that out so you know exactly what I'm doing. It turns into 8/3 plus 4 plus 1/3 and then plus 2. So actually I could go ahead and add those fractions up first. 8/3 plus 1/3 is 9/3, which is just 3. So then 3 plus 4 is 7. 7 plus 2 is 9. Even though we are kind of talking about area when we integrate, if it's not really set up as an area type of problem, you don't have to put units squared or anything like that. It can just be 9. Okie doke. Any questions about that? Plug in upper bound first, then lower bound, and subtract. Got to keep track of that minus sign. Let's try another one. Example 2, we are integrating from 0 to 2. You're going to find that it's really nice when one of those bounds is 0, because plugging in 0 is really easy to do. The function we're integrating is 2x minus 5 with respect to x. So again, start by just integrating. You can keep the 2 out front while you integrate x, or you can think of that as x to the first. So that's like an x squared over 2 minus 5x. And I'll probably want to simplify that a little bit. Those 2's can drop out, and so it's just x squared minus 5x. We're taking it from 0 to 2, but remember you have to plug in, bless you, you have to plug in the upper bound first, always. So 2 squared minus 5 times 2, that's just plugging in the upper bound, minus plugging in a 0 up there. You really don't have to show all this work because everything in the back just turns into 0. So subtracting 0 doesn't change anything. You're basically just taking 4 minus 10, which is -6. Now, as far as area is concerned, it's kind of weird to get back a negative answer when you're talking about area. The reason it's negative is because if you graphed that line, y-intercept of -5, slope of 2, actually the distance between it and the x-axis between those two values is under the x-axis instead of above. You can graph it if you want. Only look between 0 and 2. And again, that area is actually below the x-axis. That's why we get back a negative. You don't really have to worry about that too much right now. Just leave it as negative. Sometimes that happens. Alrighty, any questions about that one? Not too bad. I think I've got just a couple more actually. But this one, as you can see, is a little bit more complicated than the first two. So let's see what we can do with number 3. We're integrating from 1 to 4. And it's x cubed minus 2x squared plus 3x all over the square root of x dx. Okay, I don't like how any of that looks. So before I integrate, I'm probably going to have to simplify this a little bit. So we've had this type of function several times in calculus. We had it with derivatives, we had it with integrals. And so here's what I'll do. I'll basically take each term on top and divide it by that square root of x, except I'm not going to leave it as square root of x. I'm going to think of it as x to the 1/2. So x cubed divided by x to the 1/2 minus, let me go ahead and just leave the 2 on top for a second. That'll be 2x squared over x to the 1/2 plus 3x over x to the 1/2. And I'm really not done simplifying. I'm going to continue this on the other side. But now I have to think about what to do with those x's. We actually just talked about this in algebra the other day. Anytime you divide with the same base, you subtract your exponents. Now, it might be helpful to think about common denominators. So maybe think of the 3 as a 6 over 2. That's a 6 over 2, kind of hard to see right there. So 6 over 2 minus 1 over 2 would be 5 over 2, or 5/2. And that's actually not integrating yet. That's still just the original function. Now for the second part, I'll keep the 2 there, but I probably want to think of the exponent. It was a 2, so think of that as a 4 over 2. Now, 4 over 2 minus 1 over 2, forgot to put the x, that would be x to the 3/2 power. So we're looking pretty good. Keep the 3 there for the last part. And since this is like x to the 1st power, you would think of the 1 as a 2 over 2. So 2 over 2 minus 1 over 2 is another 1 over 2. So that's just 3x to the 1/2. Now comes the integration. Haven't even done that part yet. Sometimes the first part of simplifying is the hardest part of the problem. Now let's see what we get. Add 1 to my power. So the power right now is 5/2. So think of the 1 as 2/2. You've got 5/2 plus 2/2, which is 7/2. Put the new power on bottom. Don't forget to do that last part. Now subtract 2 times, I'm going to just kind of put that 2 out front for a second. If I add 1 to a 3/2, it's like adding a 2/2, which makes it 5/2. I'll try to make all that look a little bit better here in a second. And then plus 3 times x, that would be to the 3/2 over 3/2. So I added 2/2 to a 1/2. That's what gave me 3/2. So flip that over, it becomes 2/7 x to the 7/2 power minus, sometimes this is tricky right here, if I flip over this fraction, it becomes 2/5, but the 2 on top and the -2 right there, you can turn that into a -4/5, and then it's still just x to the 5/2 power. Same kind of thing happens right here. It's actually a little bit nicer though. If you turn that into a 2/3, 3 times 2/3, the 3's would drop out and you'll just get back 2. Now still, this is a definite integral, so I still need to plug in the 4 first and then the 1. Any questions up until that point? Calculators will be our friends here for this next part. I've got 2/7 times 4 to the 7/2 power minus 4/5 times 4 to the 5/2 plus 2 times 4 to the 3/2. Now that, again, with the subtraction, from there you subtract everything that you get when you plug in a 1. Now actually, I'm going to take a little kind of shortcut, I guess. What is 1 to any power? 1. 1 to the 7/2 power is 1. 1 to the 5/2 power is 1. 1 to the 3/2 power is 1. So all of those parts turn into 1, which means I'm just basically going to get back those numbers out front. 2/7 minus 4/5 plus 2. If you're not sure about that, anytime you're not sure about something like that, try it on your calculator. 1 to the 7/2 power, 1. 1 to the 5/2 power, 1. Those are all just 1s, so that's a little bit nicer. But I guess I should pick my calculator back up for this part. What I'll probably do first is, there's a lot of fractions going on up here, I'll probably work on the exponents first. So maybe leave 2/7 alone and let me figure out what 4 to the 7/2 power is. That's a 128. So I'll keep multiplying that here in a second. I'm going to leave the 4/5 there and take 4 to the 5/2 power, which is 32. And then leave the 2 there. Take 4 to the 3/2 power and you get 8. Now, if you want to go ahead and distribute that minus sign, you can. That'll be a minus 2/7 plus 4/5 minus 2. Now, I'll probably go ahead and try to do the rest of that, or just all of that, on my calculator. So I'm just typing in, and actually you can do it a couple different ways, but I'll probably just put the 2/7 kind of in parentheses so my calculator knows what I'm doing. 2 divided by 7, and then that was times 128. So there's that. Then the next part, I'm going to just keep going back to this so I remember. 4/5, you could go ahead and turn that into a decimal if you wanted, or type it in parentheses like I did the last one. Try this with me. Make sure you get back the same thing. So then the 4/5 gets multiplied by the 32, plus that'll be 16 minus 2/7 plus 4/5 minus 2. Finally, we get back a decimal, which is fine with me if you want to leave it as a decimal. It's like a 25.49. If you want to even say 25.5, that would be fine. Again, upper bound first, then lower bound. Subtraction was a little bit nice there, though, with all the ones. Hello? Question? Okay.
This one, we just had to find the right side, right?
Just the right on that one, yes. Do you want to fix that? Okay, that's fine. Any questions about number 3? Alrighty, I've got one more for us. I know, Hannah, you have to leave. I'm going to be putting this on the website for Gia because she's gone. So if you want to look on there for number 4, it'll be there. All right, last one. Example 4. I promise not as complicated, but there is a square root. It's the integral from 1 to 9 of the square root of 3 divided by x dx. Now, once we finish this example, I am going to show you something you can do on your calculator to kind of check your answers. So don't put your notes away just yet if you finish this a little bit early. But I do probably need to rewrite that a little bit before I can integrate. The issue is the gigantic square root and the fact that the x is on the bottom of that fraction. So watch what I'll probably do first. I'm going to break that square root apart and turn it into the square root of 3 over the square root of x. Now, whenever I continue this, I'm not quite ready to integrate yet, but remember, square root of x is the same as x to the 1/2 power. So if I pull that up so it's not on the bottom of my fraction anymore, now I can write it as square root of 3 times x to the negative 1/2 power. Remember, we don't really have like a quotient rule for integration, so anytime you have a quotient, you have to do something to simplify it. Now, even though the 3 is under a square root, it's still just a number, so I'm just going to leave that number out front while I integrate x to the negative 1/2. So here we go. Add 1 to my power, negative 1/2 plus 2/2, that's a positive 1/2. Put my new power on bottom. Now, once I flip that 1/2 over, it turns into a 2. So I'm just going to write this as 2 radical 3 x to the 1/2 power. You really can't take the 2 and the 3 and multiply them since the 3 is under a square root. So that's probably all I'll do for that. Now, think about plugging in the 9 first. I'm going to show all of my steps here so you can see exactly what's going on. I replaced x with 9, then I subtract and I replace x with 1. So we mentioned this earlier, and we've done this a lot in calculus, but remember, a 1/2 power is like a square root. So square root of 9 is 3, and in the back, square root of 1 is 1. You could do that on your calculator too if you wanted. So I'm actually going to try to leave this as exact as possible. You can take the 2 times the 3 right there, and make that 6 radical 3 minus, technically I'm taking the 2 times the 1 there, that would be 2 radical 3. And it's been a while since we've subtracted radical expressions, but it's kind of like having like terms. They both have a radical 3, so you leave the radical 3 alone and just subtract the numbers out front. A decimal wouldn't be like totally wrong on that one, but it is kind of nice to keep it exact if possible. Now, the part that you'll enjoy seeing is the part where you can check this on your calculator. So if you don't have one yet, I'm going to pull mine up here so you can see what I'm doing. If you have one with you, make sure you've got it out. I always have to warn before I show this. This actually, can check like the whole problem for you. It will spit out the answer for you, which is nice when you're checking. But I want to make sure you know on homework, on tests, on quizzes, anything, you got to show the steps for each problem to get your credit. You can't just have the answer because then I'll think you probably just did it on your calculator. So if you've got yours in front of you, and mine's an 84, so if you have an 83 especially, we're going to have to do yours a little bit different. But for most 84s, you're going to go to math, the third button down on the left there. And for me, it's option 9. It should have like INT somewhere in it. That's the integration function. So I'm going to hit 9. And looky here, you can pretty well just type in what you need. You need it from 1 to 9. So there's my bounds. I want the square root of, it was 3 divided by x. Looks a little bit different, but that should be fine. And then dx. So once you set that up and fill it in, our answer was in radical form. What did we get? We got 4 square root of 3. So you actually might want to type that in as well just to make sure it's the same, and it is. Now, having shown you that, again, I have to say on a test, on a quiz, especially on a problem like this, you need to show how you simplified it. You need to show what you got after you integrated. And I also want to see this step where you plug in your bounds. Now, I have in the past done something like I think I did back in chapter 1, where like part of the test you can use your calculator, the other part you can't. So we do that sometimes in chapter 4 too, just to make sure that you actually know how to work with the definite integrals. But again, feel free to use your calculator to check. So this is the assignment. If I do a homework check tomorrow, there needs to be work with all of these. Can't just put the answers down. It should be C78 from page 328. We're doing numbers 5 to 18.